In our topic today in physics, we'll be looking at characteristics of sound and vibration in pipes. The basic characteristics of sound are 1. Pitch, 2. Intensity, 3. Quality, 4. Loudness, 5. Beats. We want to look at pitch as one of the characteristics of sound. Pitch depends on the frequency of the wave. A low-pitched note has a low frequency, while a high-pitched note has a high frequency. What are we talking about? When the frequency of the wave is low, the pitch is also low. When the frequency of the wave is high, the pitch is also high. Intensity of sound is also one of the characteristics of sound. Intensity of sound is the rate of flow of energy per second by unit area perpendicular to the direction of propagation of the sound wave. Intensity of sound, denoted by letter I, is proportional to the square of amplitude, A squared here. This is because energy depends on the amplitude. Intensity of sound, I, can be expressed as energy over area times time. If you look at this equation, energy over time is actually power. So we can also express this as the average power over area. Quality of sound. This depends on the overtones or harmonics accompanying the main or fundamental notes. Overtones are notes of higher frequency than the fundamental frequency, but with smaller amplitude. Beats. This is a periodic rise and fall in loudness or intensity. Beats can be expressed as F of B, which is equals to F2 minus F1, where F of B is the beat frequency. F2 and F1 are the frequencies of two sources of sound sounded together. Our next subtopic is vibration in pipes. Open and closed pipes. The vibration of air columns inside a pipe forms the basis of the operation of wind instruments such as trumpets, flutes, or pipe organ. The column of air in a pipe has a natural frequency of vibration, which depends on the length of the pipe. The notes result from stationary longitudinal waves set up in the pipe with the closed end as a node and open end as antinode. Here we have a closed pipe The antinode is at the open end, the node is at the closed end. And from here to this point is the distance of the pipe. L is the length of the pipe. A there stands for antinode, and N here is for node. The distance between A, which is the antinode, and N, which is the node, is lambda over 4, which equals the length of the pipe, and is given as lambda over 4, which is the length of the pipe. If you make lambda here the subject, then you have 4L. The fundamental frequency F0 is given as the frequency of the sound over lambda. But lambda is given as 4L. Therefore, by substitution, the value of lambda, which is 4L, will now be substituted here. And fundamental frequency F0 will now be given as velocity of the sound over 4L. By blowing the air harder in the pipe at the open end, overtone can be produced. If you look at the diagram, L is the length of the pipe. We have the antinode at the open end there. We have another antinode here. We also have the node, and then we have another node at the closed end. Now the distance from this node to this node here is given as lambda over 2. And the distance between antinode and node is given as lambda over 4. Now if you combine the two distances, you have NN plus NA, where NN is lambda over 2 and NA lambda over 4. Summing them together, we have 3 lambda over 4. Therefore, the length of the pipe here will be given as 3 lambda over 4. If you make lambda the subject, you are going to have 4L over 3. The first overtone has a frequency F1 given by this expression. F1 is equal to velocity over lambda, which can also be expressed as 3V over 4L. From the fundamental node, F0, which is the fundamental frequency, is given by V over 4L. If you put V to be 4L F0, that is 4 times the length of the pipe and the fundamental frequency of the first overtone, we have F1, which is equal to 3F0. This is the first overtone. Therefore, F0, 3F0, 5F0, 7F0, etc. are the possible harmonics in a closed pipe, indicating that closed pipe gives odd harmonics. Note, harmonics are frequencies which are multiples of the fundamental frequency from a musical instrument. Let us look at open pipe. If air is blown into an open pipe, the open end always forms the antinode, since the air can move freely there. Here is the diagram of an open pipe. You can see that both ends are not closed, they are all open. The distance from here to this point is the length of the pipe. We have the antinode at the open ends there, and we have the antinode at the other open end. And here is the node. So the distance between here and here is what we have as lambda over 2. And it's actually the length of the pipe. If you make lambda here the subject, you are going to have 2L. By simple cross multiplying this, you have lambda as 2L. The fundamental frequency, F0, as usual, is given as the velocity of sound over the wavelength, lambda. And by substitution, we have lambda to be 2L. Therefore, we can substitute here the value of lambda, which is 2L, in this one here. So the fundamental frequency now will be V over 2L. The open pipe can be made to produce overtone by blowing harder. If you look at the diagram again, we have antinode at the open end, and then we have another antinode here, and then we have another antinode at the other end. The length of the open pipe is there as L, and then we have a node and a node at that point. The distance from here and this, which is the antinode, is given as lambda, and it's also the length of the pipe. The frequency of the first overtone is given by F1, which is V over lambda. Therefore, F1 can also be written as V over L. F1 is now given as 2F0, which is 2 fundamental frequency. Other overtones can be produced, such as 3F0 can be produced, 4F0, etc. The possible harmonics are F0, 2F0, 3F0, 4F0, 5F0, on and on and on, indicating that open pipe has all harmonics, both odd and even. So in open pipe, we can have both odd harmonics and even harmonics. Example 1. A pipe of length 45 centimeters is closed at one end. Calculate the fundamental frequency of the wave generated in the pipe if the velocity of sound in air is 360 meters per second. Option A, 5.5 Hz. Option B, 148.5 Hz. Option C, 200.0 Hz. Option D, 550.0 Hz. Now solution. Fundamental frequency is what we are calculating. Then the velocity of sound in air, V, is 360 meters per second. And the length, L, is given as 45 centimeters. We are going to convert this length into normal units, which is 45 over 100. And that is 0.45 meters. Now we can write the formula. The formula here is F naught is equal to V over 4L. By substitution, V is 360 over 4 times L is 0.5. 0.5 meters. And that gives us 360 over 1.8. 360 divided by 1.8. The answer there is 200.0 Hz. That is the correct option. So option C is the correct option in this example. Example 2. The pitch of an acoustic device can be increased by A, increasing the frequency, B, decreasing the loudness, C, increasing the amplitude, D, decreasing the intensity. The correct option here is option A. Pitch of a sound wave depends on the frequency. So it's not on loudness. Pitch doesn't depend on loudness of the sound. It doesn't depend on the amplitude of the sound. It doesn't depend on the intensity of the sound. So the correct option is option A. Increasing the frequency will increase the pitch of the sound, and decreasing the frequency will also decrease the pitch of the sound. So option A is the correct option. Example 3. In a closed organ pipe producing a musical note, an antinode will always be produced at A, the closed end, B, the open end, C, middle, D, all parts of the pipe. The correct option is option B, the open end. Antinode is produced at the open end and not at the closed end. At the closed end of a pipe, a node is produced, not antinode. So the correct option is B. Antinode is produced at the open end, not closed end or middle of all parts of the pipe. Is at the open end. Example 4. The frequency of the beats produced when two tuning forks of frequencies 258 Hz and 270 Hz are sounded close to each other is A, 600 Hz, B, 12 Hz, C, 264 Hz, D, 528 Hz. Solution. Bit frequency is given as f of 2 minus f of 1. This is the bit frequency, and this here is the higher frequency, and this is the lower frequency. So f of 2 is 270 hertz. F1 is 258 hertz. Putting these values in the right position, we have bit frequency there as 270 minus 258. 270 minus 258. The answer is 12 hertz. So bit frequency is 12 hertz. The correct option here is option B, which is 12 hertz. So option A, option C, and D are not the correct options.